Hey guys, in this video we're going to talk about how we use Gauss's law to find the electric field around a plane. The first thing we need to begin with though is just generally what do we expect the field to look like around a plane, because that actually ends up being pretty important in the derivation that we're going to do. So we've learned before that around something like, say, a sphere, you have an electric field that, assuming it's a positive sphere, goes outwards in all directions. So not just the way I've shown it, but like, flat, right? Where the electric field is only going left and right and up and down, but, also the more difficult things to draw, like this line's coming out towards you, right? Okay, but you get, I hope, the idea, right? The lines are coming out in all directions, right? Some are coming towards you, some are going away from you, right, off into the distance. So the lines are coming off of the plane, off of the sphere in all directions. In the past, when we've looked at something like a cylinder, we said if you were doing a side view from a cylinder, you get something like parallel lines near the middle of it, but it starts fringing out near the edges, a little bit like that. Of course, when we do Gauss's law, we're only ever looking at the middle of a very long cylinder, right? So we're only looking at this middle section where the lines are coming out straight left and right. If you're doing a top-down view of a cylinder, though, it looks just like our sort of one-dimensional view of a sphere, right? The lines are coming radially outwards. But near the middle, viewed from the side, they make basically parallel lines. Now, elsewhere in your textbook, you may have heard of things like, quote, uniform electric fields. A uniform electric field is one where the field lines are, all drawn uniformly spaced like this, because the spacing indicates that the field strength is uniform, right? If the spacing doesn't change, then that's a field which is of constant magnitude everywhere. But we've already learned that cylinders don't give you a constant electric field, right? It follows usually something like, say, this formula, or at least this is one of them, right? It's got an over R in there. So the field isn't constant, it decreases as you move away from it. That's not obvious from the two-dimensional, sideways view that I gave you here, but it does become obvious if you're looking down from above, right? Whereas this spacing doesn't appear to change. It's obvious that when you view the cylinder from above, the spacing does change. What kind of a shape would it take to give you, like, really a uniform electric field? Meaning the spacing of those lines is exactly uniform because the lines are parallel in every possible dimension. Well, okay, the whole video is about planes, so yeah, you guessed it, planes are in fact how you get a perfectly uniform electric field where the lines all come off parallel, not just in one or two dimensions, but in all dimensions. This is what we're talking about, right? The field lines coming off of this plane here are uniformly spaced, both, horizontally in the x direction and in the z direction as you move away from. If this is a positive sheet of charge, of course those lines are coming up, right, coming away from it on the top side. But also note, I should draw field lines down below it because, well, there's no reason it wouldn't make a field below it as well. All right, so there you have it. Lines going up, lines going down, because this is a uniformly charged sheet of positive charge. All right, now if we want to use Gauss's law to find the electric field above and below this plane of charge, we first have to figure out what Gaussian surface we're going to use. The most common shape that people will use when they're trying to determine this formula is actually a cylinder, oddly enough. Which may seem like a weird choice, but frankly, any prismatic solid will do. I mean, literally any prismatic solid. Some textbooks will just actually be deliberately obnoxious and have you do some just absolutely off-the-wall shape like that, simply because they're trying to make the point that it literally doesn't matter what you use as long as it's not something dumb like a sphere. All right, now the idea with Gauss's law and the A part of it right there, remember, is that is the surface area of the Gaussian surface through which there is flux. So it's not just the area of the Gaussian surface, but it's only those sides of it that actually have flux through them, which is why we want to use any prismatic solid, because we want all of the field lines to either cross perpendicularly or be parallel to all the faces of our chosen Gaussian surface. Yeah, let me just draw a bad shape for a moment off to the side here, right? Here's my field lines coming off. If I chose to use a spherical Gaussian surface, this would be a horrible idea because then we would have to actually worry about the fact that this is a dot product technically, and not all of those lines are crossing my Gaussian surface perpendicularly, right? There's some kind of an angle here at which that crosses. And then since every single field line would cross at a slightly different angle, that actually suddenly becomes a calculus problem, and oh, no thank you, no thank you. All right, with my simpler diagram, it's going to be easier to show which surfaces of my chosen Gaussian surface, which happens to be a cylinder, have flux through them, and which ones don't. Well, since the lines coming off of the plane are only going up and down, we have flux through the top face, which I'll shade in green. There, enhanced clarity. All right, and, and the bottom, right? The lines are also going down, and my Gaussian surface, if you can understand this from my dotted lines, is going through the actual plane. There's flux through the top of it and also through the bottom of my Gaussian surface, because some lines are going through the top, some are going through the bottom. There is, however, no flux through the curved surface area. So when I talk about the area through which there is flux, I'm not using the formula for a cylinder. I would be using, I suppose, technically like the area of a circle, right? I would say there's the area of the top, the area of the bottom. Pretend I don't know the area of a circle for a moment. The area through which there is flux is 2a. All right, now this takes me back to, why do some books use that? Why do some books use just an absolutely arbitrary shape? The answer is because it doesn't matter what the area of the object is, okay? The area through which there is flux is 2 times whatever the area of the base is. But won't that formula matter at some point? Well, actually, no, it won't, because now we're going to do Q enclosed. Since it's a sheet of charge, we're using sigma. Sigma is Q over A. That means that the Q enclosed is going to be sigma, whatever the surface density of the sheet is, times A. Wait, is that the area of the sheet? No. Remember, it's Q enclosed. The area of the sheet that's actually enclosed, I shall now shade in yeller. That's yellow for those of you that, didn't understand me there. There, yellow. That would be circle, since I drew a cylinder, but it would be one, whatever the heck this thing is, if I was using that absolutely arbitrary prismatic solid. Or it'd be like one square if I was using like a cubical Gaussian surface or something like that. Whatever, it doesn't matter, because what you should be able to see now in the algebra is this factor of A cancels. All right, now a rookie mistake people make is this. They will say, Q enclosed, oh yeah, that's sigma A. Oh look, I've got an A here, I've got an A there. Cancel the A's. Don't cancel those A's. They represent different areas, okay? This one was the area of charge enclosed. That was the yellow area, okay? This one over here represents the surface area of the Gaussian surface through which there is flux. That would be the top and the bottom. So there's twice as much area with flux through it as there is area of charge enclosed. Precisely twice as much area. Therefore, my electric field is ultimately going to be sigma, the charge density, whatever that is, over 2 epsilon naught. All right, now if you're wondering why someone might get excited about that answer, it's because there are no variables in it. What that's saying is the electric field is uniform, which is what we set out to prove in the first place, right? Since the field above a plane is uniform, it doesn't vary with distance, and that's what we were trying to show in the first place. If you're now trying to apply this to questions that you see on the homework, remember you would do this derivation every time you see it. And you would use this to solve for the electric field necessary to, say, like levitate something above a Gaussian, or excuse me, above a plane of charge, right? That means you'd be doing something like QE equals mg. And now you know the formula for the electric field, and so you can solve for electric field or something like charge density, whatever it is they're asking for. All right, that's enough for now, and good luck with the physics homework.